Good morning, everyone. This is Sanvita from IRE College, studying civil engineering in second semester. So today I am going to explain a topic from ordinary differential equations and vector calculus. So moving into the topic, my topic is to solving the equation after making it exact. The hidden solution. So discover the elegant transformation that unlocks solutions to seemingly impossible differential equations. So today I am going to explain how do we solve the equation after making it exact. So after making the equation exact, we have to solve the equation. So I'm going to explain how it is going to be solved. So moving on, the mystery when equations aren't exact. So many differential equations can be written in standard form, which is mx of y I and dx plus n of xy I dy is equals to 0. So however, not all of these equations are exact. A crucial property that determines whether they are directly represent the total differential of some function f of xy. When an equation isn't exact, finding a simple implicit solution f of xy is equals to c becomes significantly more challenging. So if you think of it like trying to solve a puzzle without all the pieces fitting perfectly, the pieces are there, but they need to be transformed first. So here are some examples of some 2-mark questions, 7-mark questions, 5-mark questions, along with some 11-mark questions. Like what are ordinary differential equations? Given that dy by dx plus y of tan x is equals to e power 2x cos x comma y of 0 equals to 2. You have to show that the solution of the above differential equation is y is equals to half of e power 2x plus 3 into cos x. This is an example of a question. And moving on, the exactness test or detective skill. So, a critical condition is that an equation m of xy I dx plus n of xy I dy is equals to 0 is exact if and only if dou m by dou y is equals to dou n by dou x. So, this is the condition where it is exact. So, firstly, to solve an equation, the equation should become exact. So for the condition of becoming the equation exact, an equation called m of xyi, comma dx plus n of xyi, comma dy is equals to 0 is exact if and only if the condition solved, which is dou m by dou y is equals to dou n by dou x. So why this matters? So this condition is like finding a crucial fingerprint that proves the equation as a solvable in a specific elegant way. It's the mathematical equivalent of discovering that two different paths actually lead to the same destination. So in the exactness test passes, we know that exists a potential function f of xy that holds the key to the solution. So the aha moment when you find the potential function f of x, comma y. So in exactness test passes, we know there exists a potential function f of x, comma y that holds the key to the solution. So basically, there are two relationships and solution we have. So the first relationship, second relationship, and solution. And coming to the first relationship, dou f by dou x is equals to m of xy. And second relationship is that dou f by dou y is equals to n of xy. And the solution is finally the general solution is simply f of xy is equals to c. So this elegant result means that once we have verified exactness, we can reconstruct the potential function by integrating either m or n and matching terms. So moving on, the challenge. What if it's not exact? Now here comes the question. As I've explained you, how do we solve a equation which is exact? I've explained the conditions of exact differential equations. Now the challenge is that how do we solve an equation if it's not exact? So the bad news and the good news here. So the bad news is that when a fraction of partial differentiation of m and partial differentiation of y, which is dou m by dou y and dou n by dou x is the equation is inexact, which means there is no potential function f of xy, where here dou m by dou x is equals to dou n by dou y, which is the condition for exact, and dou m by dou x is not equals to dou m by dou y is the equation of non-exact solutions. So here, this equation has no potential function f of xy. So that satisfies both partial derivative conditions simultaneously. The standard method fails and we face a seemingly insurmountable obstacle. And the good news is that don't despair. We can often transform an inexact equation into an exact one by multiplying through by a carefully chosen function called an integrating factor. So basically, we have to convert inexact equation into an exact equation. Why? You have to choose a function which is called as an integrating factor and you have to multiply it through it. So this transformation is like finding a secret key that unlocks a locked door. The problem that seemed impossible suddenly becomes solvable. So the integrating factor method is one of the most powerful techniques in differential equations. So it transforms an inexact equation into an exact one through multiplication. So the integration factor, gambit, turning the tables. So there are 4 steps here. So which one? First one is finding mu of x comma y. So you have to discover a special integrating factor function. And second one is that you have to multiply the equation. Mu of x comma y, I of m of x comma y I dx plus n of x y I dy is equals to 0. And you have to verify the exactness. So the new equation is now exact. And the fourth one is that you have to solve as before. Apply the exact equation method to find f of xy equals to 0. So these are the 4 steps of the integrating factor method, which is one of the powerful techniques. So first step is finding mu of x comma y, and the second one is multiplying the equation, and the third one is verifying the exactness, and the fourth one is you have to solve the equation. Moving on, finding the integration. So for many common cases, the integrating factor depends only on x or only on y, so which dramatically simplifies the calculation. In the case 1, you have mu depends only on x. Here you got mu of x is equals to exponential of integral dou m by dou y is minus dou n by dou x by n of dx. And in the case 2, it depends only on y. Mu of y is equals to exponential of integral dou n by dou x minus dou m by dou y by n of dy. So in both of these cases, you have to, if neither condition holds, the integration factor may depend on both x and y, making it much more difficult to find. However, the cases above may cover many practical applications. Okay. So the grand finale, you have to solve the transformed equations. And the first one is you have to multiply by mu of x comma y. And the second one is define new functions. And the third one is verify exactness. So coming to the first one, multiply by mu of x comma y. You have to transform the original inexact equation by multiplying through by the integrating factor. And the second one is you have to define new functions. Let m is equals to mu of m and n is equals to I of mu of n. So you have to verify the exactness. You know how to verify exactness, which is partial fraction of dou m by dou n is equals to dou n by dou y. You have to find f of x comma y. You have to integrate to find the potential function for this new exact solution. And then you have to write the solution. The general solution is f of x comma y is equals to c. So there are 5 steps. Multiply by mu of x comma y, define new functions, verify exactness, find f of x comma y, and you have to write the solution. So let's work through a concrete example where the equation happens to be already exact. So demonstrating the complex solution process. And the first step is you have to identify both m and n for the given equation. Here m is equals to x square plus y square and n is equals to 2xy. You have to apply the exactness text for it, which is dou m by dou y is equals to dou n by dou x. So here they are equal. The equation is already exact. And now you have to integrate m with respect to x, which is f of x is equals to x square y plus, integration of f of x is equals to x square plus y square, where f of xy is equals to fraction of 1 by 3, where x cube plus xy square plus ky. And now we have to differentiate with respect to y, which is integral f of y is equals to 2xy plus k of y. And you have to set equal to n. 2xy plus k of y is equals to 2xy. And you have to solve for k of y, which is k of y is equals to 0, which implies k of y is equals to c1. So you have to now write the final solution. Fraction of 1 by 3 into x cube plus xy square is equals to c. Now the equation is solved. So the power of transmission of equations. So exact differential equations and the methods to make them exact provide a powerful toolkit for solving a wide range of problems in science and engineering. So the integrating factor technique is particularly remarkable because it transforms seemingly impossible problems into solvable ones. It's about recognizing patterns and applying the right transformation to unlock hidden solutions. The key takeaways of this are you have to always test for exactness first using partial dou m by dou y is equals to dou m by dou n by dou x. When inexact, look for an integrating factor that depends on x or y alone. The method works for many practical applications in physics, engineering, and economics. So the integrating factor method transforms the impossible into the routine, revealing that many differential equations are simply exact equations in disguise. Let's recall what we have discussed before. We have discussed how to solve the equation after making it exact, about the hidden solution. And now we have discovered the mystery when equations aren't exact, which is dou m by dou y is not equals to dou n by dou x. And you have to make the exactness text, which is dou m by dou y is equals to dou n by dou x. And the equation m of x comma y I dx plus n of x comma y I dy is equals to 0 is exact if and only if this condition is satisfied. And how do we find the moment potential fraction of f of x comma y? First relationship, second relationship, and solution with dou f by dou x, dou f by dou y, and the general solution f of x comma y is equals to c. And we have known about the challenge. What if it's not exact? The bad news and the good news. And we have also discovered how to integrating factor gambit, turning into tables. So finding the mu of x comma y, multiplying the equation, verify exactness, and solving as before. And the next one is we have discussed two cases when it depends only on x and when it only depends on y, which is mu of x is equals to exponential of integral dou m by dou y is equals to dou n by dou x by n of d of x. And the next case is mu depends only on y, which is mu of y is equals to exponential of integral dou n by dou x minus dou m by dou y by m of dy. In the next one, we've discussed 5 steps: multiplying by mu of x comma y, defining new functions, verify exactness, and find f of x comma y and write the solution. And next we have discussed one already exact solution. How do we solve the exact differential equation? And these are the key takeaways and the power of transformation. Thank you.